So the metric tensor not being positive definite means you can't really have an obvious notion of spatial distance immediately. You have to, do something smart. And that is talk about three-dimensional submanifolds that are Riemannian, and where the metric tensor restricted to those submanifolds is positive distance. So then you can talk about, you can have a notion of distance that makes sense. Making sense meaning, when you're talking about actual distance, it shouldn't be possible for it to be negative or 0 unless they're at the same point. So that has to do with defining a notion of simultaneity. What three-dimensional submanifold are you looking at? That's what simultaneity really is. And doing that is difficult, at least in terms of, there's a lot of choices of three-dimensional Riemannian submanifolds. So a time-like geodesic observer has all these coordinate systems available to her, each with a different time coordinate. If you fix that time coordinate, you're talking about simultaneous events, which lets you have a notion of distance, but that's a coordinate-dependent notion. And we want to talk about things that are, that should be, if you want to talk about the distance from yourself to some other point in space, you don't want that to depend on coordinates. You want it to be a number that makes sense. The way it's normally done in cosmology is going back to that metric I showed you. If you fix the normal time or cosmological time, t, that generates this submanifold. Coming up there's a picture of it. But you fix this time, right, and you get this submanifold that I call M sub t. The problem with doing it in the way it's normally done like that is that a time-like geodesic observer sends out a space-like geodesic. Geodesics are just good paths. They're the generalizations of straight lines, if you haven't seen that word. So you send out the space-like geodesic along the submanifold you generate. You're like, all right, cool, I can define distance. It'll make sense on this submanifold. But then you zoom out and look at that path in the full manifold M, and it's not a geodesic anymore. So it doesn't, I don't know, that seems problematic. It seems like maybe that isn't a good definition of distance. Here's a picture that goes with that. So you can take all these different slices, and any one of them could be the submanifold that you define distance on. But if this is the one you pick, and you have this curve along it, then when you zoom out, and that curve's no longer a geodesic, it's like, it felt straight on this, but then in the ambient space it doesn't feel flat, it doesn't feel straight anymore. This guy here is a different submanifold that you could get, called the Fermi space slice. So if you have a geodesic observer, and we're going to be talking about Fermi coordinates, the Fermi observer in our space-time, the Fermi space slice is all space-like geodesics, in a sense, orthogonal to the observer's velocity. Now, a geodesic path can't really be orthogonal to a vector. They live in different places. So what that means is you define this function, which is just inner producting your observer's velocity with this. I'll explain this function in a sec, but it basically relates geodesics to vectors in the tangent space. And so it lets you make precise what I said that was vague when I said that you find geodesics orthogonal to the observer's velocity. So this is an inner product. When it's 0, these things are orthogonal. So look at all the points where this does give you 0, and the geodesics corresponding to them generate this submanifold called the Fermi space slice of tau simultaneous events relative to the geodesic observer gamma at proper time tau. But I'll probably just say these first 3 words and imply the rest. And there's a notion of distance on this submanifold, and it's this. Again, I'm going to explain what the exponential function is on the next slide, but it can be shown to be the proper distance along this submanifold. The exponential map I was just talking about takes lines through the origin of the tangent space, sends it to geodesics through the point. You can show, for example, in O'Neill's semi-Riemannian geometry, that given a point and a vector in the tangent space at that point, there's a unique geodesic that goes through the point and at the point, its velocity vector is the vector you're originally considering. And so the exponential function sends vectors in the tangent space down to geodesics using that proposition on the previous page. So it's very useful. It lets you go from the tangent space down to the manifold, and it relates geodesics to vectors, which is like doing that. Here's a picture demonstrating that. You have some vector and a point. The exponential function sends this vector, sort of projects it down onto a geodesic. Okay, so Fermi coordinates. What are they? The geometric way to think of them is think of them as the coordinates on these Fermi space slices. But here's how you construct them. A Fermi coordinate system along the path of a time-like geodesic observer, which I should say more clearly what that means. If you're just sitting there in space, flying through time, but not moving in spatial dimensions, you're a time-like geodesic observer, for example. So a coordinate system along your path there, because you are moving, you're just only moving through time, would be this. It's parallel along the world line, the path, and this first vector is the velocity vector, the forward velocity of the observer, and then you get a Fermi coordinate chart in the following manner. There's a picture on the next slide that gives you a better idea of what I'm talking about here. I can't actually in 2 dimensions draw what 4 mutually orthogonal vectors would look like, but pretend these guys are all mutually orthogonal. And so the idea is you just have this coordinate frame that moves along with your observer. And yeah, these are all orthogonal to each other, so they cover, you can find places on that Fermi space slice with them. Okay, so I'm going to go down to 2 dimensions now, because as you saw there, it's hard to draw 4 dimensions. If you fix, again, we're assuming everything's homogeneous, isotropic, it doesn't matter which direction I look, so just pick an angle to look in, and then the metric reduces down to this, it's easier to look at. If you have, again, a geodesic observer, you fix some time, tau, and now there's only one space-like geodesic coming out of the observer's path. So A of t again, it's increasing. That was Hubble's result, so we're going to use that result. We pulled this parameter out of our hat because it's useful. That's the only reason. And so we parameterize the geodesic with it, sigma. Okay, and so Dr. Klein and Evan Randalls published a paper where they give the coordinates of the geodesic in T chi, the Roberts and Walker coordinates, in terms of the tau and sigma I just showed you in the following manner. And in their paper, they showed this coordinate transformation works, is global, but assuming, they had to assume that that it was not inflationary. So, as the title would suggest, I'm going to look at when it is inflationary and a power law cosmology. This integral is not nice, generally, just to point that out. And then tau sigma are not Fermi coordinates, if that is what you're about to ask, but they're very closely related to Fermi coordinates. I'll mention in a sec that you can go from sigma to rho, which has physical meaning, and then those are called Fermi polar coordinates. So if you can get to tau sigma coordinates, you're pretty much at Fermi coordinates.
Yeah, so my question was actually, by global you meant that these 2 coordinate patches overlap across the entire domain in space-time?
If I didn't say it, Roberts and Walker, those T chi coordinates, the reason everyone uses them is because they cover all of space and time. And they showed that these coordinates, or Fermi coordinates, also cover all of space and time.
All of space.
Yeah. Provided that this was true. So, Yeah, so here's the rho I was talking about. So rho is proper distance along the space-like geodesic, and once you're in tau rho coordinates, you know that those are called Fermi polar coordinates. So this is, I'll mention later, but this is a smooth increasing function of sigma, so it has an inverse, and then you can go from sigma to rho that way. Okay, so now this looks like our parameter sigma, but we're going to fix the time on the denominator, fix Robertson-Walker time, and then vary the numerator, and then think of that as a function sigma of tau, and that lets us, for a fixed Robertson-Walker time coordinate, think of chi as a function of one variable, like this. In the case, the results are going to be for t to the alpha, so the integral that I showed on the last slide reduces to that. And more changes of variable, we can put rho into this form, the proper distance like that, which for us, where a of t is t to the alpha, looks like that. And, all right, oh yeah, that was just a reminder, because when I practiced this, I kept forgetting to say that. You can notice that you can identify points instead of by their Fermi time and their Robertson-Walker time. Though I haven't shown the Fermi coordinates actually, that they're a coordinate transformation yet, but I'm going to, and then that's an interesting observation that we'll come up with. So, at a fixed tau setting, t equals to 0 gives the following. All I did was change the lower limit to 0, and you integrate it and get this function that'll show up later. I was trying to figure out where to put him. I'm not actually going to talk about this right now, but the equation it came from was here, so this guy's going to come up later.
Well, are you going to say what it means?
Yeah, I again, couldn't decide, but it's the radius of those Fermi space slices. I'll talk about the physical interpretation more, but you send out these space-like geodesics orthogonal to your path. They end at some finite distance. Finite, and so where do they end is a valid question, and they end at Robertson-Walker time 0, but that's when the Big Bang happened. So these Fermi space slices, each of them at each tau contain points where the Robertson-Walker time is 0, that is, the Big Bang is Fermi simultaneous to all events. So you define simultaneity this way. There's like a good physical reason to do it, but this weird consequence is that the Big Bang is simultaneous in this sense to all events.